One thing has followed me for decades, longer than any equations or mathematical models I've ever built. The belief that science, given enough time and technology, will ultimately explain everything. For more than 400 years, since the scientific revolution of the 17th century, that belief seemed continually reinforced. In 1609, Galileo Galilei first pointed a telescope at the sky and discovered the moons of Jupiter. In 1929, Edwin Hubble proved the universe is expanding. In 2015, the LIGO observatory directly detected gravitational waves for the first time, confirming Albert Einstein's prediction from exactly a century earlier. Today we have the James Webb Space Telescope, observing light emitted more than 13 billion years ago, and the LHC accelerator at CERN, recreating energy conditions that existed only about n½ seconds after the Big Bang. But precisely when looking straight at that chain of achievements, a paradox begins to emerge. Humans did not evolve to understand the universe at these scales. Our senses were shaped over a few 100,000 years to serve survival on Earth, avoiding danger, finding food, recognizing familiar faces. The human eye is sensitive only to light in the range of roughly 400 to 700 nanometers. The ear detects only a narrow band of frequencies, and we have no direct perception of atoms, force fields, or the curvature of space-time. Technology, from electron microscopes to particle detectors, is merely an extension of those already limited senses. And so the crucial question is no longer whether we can measure more precisely, but this: when we extend our senses with instruments, are we truly eliminating all limits, or are we merely pushing them farther back to deeper boundaries imposed by nature itself? As a physicist who trusts mathematics and the scientific method, it is precisely that question that troubles me, because it is becoming increasingly clear that some limits do not stem from technology, but are inscribed directly into the structure of the universe. If we want to go further into the question of limits, in my view, the best way is to set aside all familiar macroscopic concepts for a moment and start from a simple physical system, just two electrons. The electron, discovered by J.J. Thomson in 1897, is an elementary particle carrying the fundamental negative electric charge of nature and having a rest mass on the order of 9/10 times 10 to the minus 31 kilograms. They appear in every atom and orbit the nucleus, determining nearly all the chemical properties and structure of the matter we encounter every day. Now imagine an experiment. What happens if we try to force these two electrons closer and closer together? Immediately, classical physics tells us two forces are involved. The first is gravity, described since 1687 by Isaac Newton's law of universal gravitation, in which the attractive force is proportional to the product of the masses of the two objects and decreases with the square of the distance between them. This is the force that keeps us on the Earth's surface, keeps the moon orbiting the Earth, and governs the motion of planets and galaxies. But at the level of elementary particles, because the electron's mass is so minuscule, it is almost unimaginable. The gravitational force between two electrons is so weak that it is practically impossible to measure directly. The second is the electrostatic force, quantified in 1785 by Charles Augustin de Coulomb's law, which describes the force between two charges as also proportional to the product of the charges and decreasing with the square of the distance. Since both electrons carry negative charge, this force is repulsive. Remarkably, these two laws have almost identical mathematical structure, allowing a direct comparison of their strengths. If we take the natural values, the electron mass, the electron charge, the gravitational constant g of about 6.67 times 10 to the minus 11, and the Coulomb constant of about 9 times 10 to the 9, then compute the ratio of the electrostatic force to the gravitational force between two electrons, a staggering result appears. The distance between the two particles completely cancels out in the calculation, and the ratio is always approximately 10 to the 42, meaning the electrostatic force is stronger than gravity by about 1 followed by 42 zeros, regardless of how close or far apart the two electrons are. In other words, gravity between two electrons would need to be stronger by many trillions of trillions of trillions of times its current value just to begin to compete with the electric force. This simple quantitative comparison reveals an inescapable truth. At microscopic scales, gravity is an extraordinarily feeble force, and that very fact leads us to a profound paradox. If gravity is so weak as to be nearly invisible in the particle world, if it is completely overpowered by the electrostatic force at the smallest scales, then why is it precisely this force that dominates the structure of the entire universe at large scales, from the formation of stars and galaxies to the evolution of the universe over more than 13.8 billion years of history? It is this very paradox that forces us to move beyond initial intuition and recognize that the strength of a force lies not only in its instantaneous magnitude, but also in the fact that it is never canceled out and can quietly accumulate as we change the scale of observation. But here I need to pause for a moment and make clear that the entire argument up to this point still rests on a very familiar implicit assumption of classical physics, and it is precisely that assumption that begins to collapse when we push the question too far. When we talk about forcing two electrons closer together, when we compare gravity and the electrostatic force using laws formulated in 1687 by Isaac Newton and in 1785 by Charles Augustin de Coulomb, we are silently assuming that particles can be placed at definite positions, that the distance between them can be meaningfully stated, and that the act of measurement itself does not disturb the physical system. This assumption works very well in the macroscopic world, but it begins to fail completely as we descend to microscopic scales. The turning point came in 1927 when Werner Heisenberg announced the uncertainty principle, one of the foundational results of quantum mechanics. This principle states that it is impossible to simultaneously determine with absolute precision both the position and the momentum of a particle. This is not a limitation of measurement technology, but an intrinsic limit of nature itself. The consequence of this principle becomes particularly severe when we try to confine a particle to a very small region of space. When we force an electron to be confined within an ever narrower region, the uncertainty in its position decreases, but in exchange, the uncertainty in its momentum increases dramatically. Intuitively, the electron cannot stay still in that cramped space. Instead, it begins to oscillate violently, a form of purely quantum chaotic motion, not caused by any classical force. This oscillation is not an abstract mathematical detail. It carries a very concrete physical consequence. It increases the energy of the system. In the language of quantum mechanics, as momentum uncertainty rises, the average energy of the particle also rises. This means that probing deeper, forcing particles closer together, inherently pumps energy into the physical system under study. At relatively large distances, this energy increase may act only as a small correction, but as we continue to reduce the distance, the quantum energy associated with the uncertainty principle quickly reaches fundamental natural energy scales comparable to the rest energy of the electron itself. And at this point, another connection must enter the picture, the connection between energy and mass, pointed out by Albert Einstein in 1905 in Special Relativity. According to it, energy and mass are not separate quantities, but can be converted into each other. In other words, as we try to descend to ever smaller scales, quantum mechanics does not merely shake the particles, it quietly increases the effective mass of the system through the energy we are forced to inject. And here we are compelled to expand the theoretical framework once more, because when the system's energy begins to rise due to quantum effects, we can no longer treat energy and mass as separate concepts in the classical 19th century intuitive sense. The key turning point came in 1905, when Albert Einstein published special relativity and introduced the famous equation E equals sine mc squared, where c is the speed of light, about 300,000 kilometers per second. This equation completely overturned the way physics understands matter, asserting that mass is not a separate immutable quantity, but merely a condensed form of energy. In the 20th century, this was clearly verified through nuclear reactions. The loss of even a tiny amount of mass can release enormous energy, as in nuclear reactors, or the atomic bombs first used in 1945. But the deeper meaning of this equation is often overlooked. Not only can mass turn into energy, but any form of energy is equivalent to a certain amount of mass. That means gravitationally, a system containing more energy will behave as if it has greater mass. Returning to our two-electron system, as we try to squeeze them into an ever smaller region of space, Heisenberg's uncertainty principle, formulated in 1927, forces their momenta to fluctuate more strongly, and that fluctuation brings an increase in the system's energy. Initially, at relatively large distances, this quantum energy is much smaller than the electron's rest mass and can be regarded as a negligible correction. But as we continue to shrink the distance, the energy due to quantum confinement rises rapidly and eventually reaches scales where we cannot ignore the E equals sine mc squared relation. At that point, the two-electron system can no longer be described simply as two light particles with fixed mass, but must be seen as a region of space containing a significant amount of energy, and therefore a corresponding amount of effective mass. This is the crucial turning point of the entire argument, because for gravity there is no distinction between rest mass and mass arising from energy. In general relativity, all forms of energy contribute to the curvature of space-time. In other words, as we pack more and more energy into an ever smaller volume, we are inadvertently creating an increasingly strong gravitational source. This completely changes the initial picture. Earlier, when comparing the gravitational and electrostatic forces between two electrons, we concluded that gravity is weaker than the electric force by about 10 to the 42, a number that seemed to render gravity entirely irrelevant at microscopic scales. But that comparison was made under the assumption that the system's mass is fixed and extremely small. Now that assumption no longer holds. The effective mass of the system increases along with the energy we are forced to inject to compress it. And since gravitational force is directly proportional to mass, the strength of gravity begins to grow in a way that classical analysis never anticipated. Importantly, this increase is not some random side effect, but an inevitable consequence of combining quantum mechanics with relativity. There is no way to circumvent it with more sophisticated measurement techniques or experimental cleverness. The very act of compressing space brings energy, and that energy brings mass. Therefore, as we delve deeper into the microscopic world, we are not only confronting strong electric forces and quantum uncertainty, we are also quietly triggering the return of gravity, this time not as a feeble force that can be ignored, but as an increasingly dominant factor, ready to govern the system's behavior as we approach the deepest limits of space and time. In ordinary intuition, shaped by 19th century physics and everyday life, gravity is always regarded as the weakest force, playing virtually no role in the microscopic world, while the electric force reigns supreme. This intuition rests on a key assumption. The mass of particles is fixed, extremely small, and unchanged when we change how we observe the system. It is in that context that the famous comparison between two electrons yields the result that the electrostatic force is stronger than gravity by about 10 to the 42, a conclusion drawn directly from Newton's 1687 law and Coulomb's 1785 law. But that foundational assumption begins to collapse when we combine quantum mechanics with relativity. Since 1905, when Albert Einstein showed the connection between energy and mass, we must acknowledge that mass is no longer an invariant quantity. And since 1927, with Heisenberg's uncertainty principle, we know that confining a particle to a smaller space inevitably increases the system's energy. When this quantum energy is concentrated into an ever smaller region, it is equivalent to increasing the effective gravitational mass of the system. It is here that gravity begins to return in a very different way, because gravitational force is directly proportional to mass. As effective mass rises, even if slowly at first, the strength of gravity increases accordingly. This may seem obvious at stellar and galactic scales, where accumulated mass over billions of years determines cosmic structure, but at microscopic scales, it produces a profound consequence. The familiar comparison between gravitational and electric forces no longer holds its original value. The electric force does not get boosted in this way, because the electron's charge remains unchanged when we compress it. Charge is quantized and has held its value since the electron was identified as an elementary particle at the end of the 19th century. Gravity, meanwhile, is sensitive to every form of energy present in the system. Quantum fluctuation energy, kinetic energy, confinement energy, all contribute to increasing gravitational mass. As a result, the ratio between gravitational and electric forces, which was once considered a gigantic and immutable constant, begins to change. At first, the change is very small and can be ignored in low-energy experiments. But as we continue to squeeze the system to smaller scales, the accumulated energy increase gradually becomes impossible to overlook. It is at this point that the foundational assumption of classical analysis collapses the assumption that we can keep shrinking distance without altering the nature of the forces at play. In reality, when we shrink distance deeply enough, we are changing the very stage on which these forces act. Space is no longer a passive backdrop, and gravity is no longer a faint supporting actor. It begins to step into the center of the story, forcing us to acknowledge a crucial point. The weakness of gravity in the microscopic world is not an absolute truth, but a context-dependent result tied to the familiar low-energy regime. If the effective mass of the system continues to increase as we compress space more and more intensely, a natural and fully quantifiable question arises. Is there a scale at which gravity, once so weak and overpowered, becomes comparable to the electrostatic force? In other words, is there a small enough distance or high enough energy where the roughly 10 to the 42 difference between the two forces, the number obtained directly from combining Isaac Newton's 1687 gravitational law with Charles Augustin de Coulomb's 1785 law, begins to disappear? This is not a vague philosophical question, but a serious physics order of magnitude estimate. We know the electrostatic force between two electrons depends only on their charges, and this charge is a natural constant that does not change no matter how much we compress the system. Meanwhile, gravitational force depends directly on mass, and the system's effective mass increases with the energy that Heisenberg's 1927 uncertainty principle forces us to inject as distance decreases. So the problem can be inverted. How much effective mass is needed for the gravity produced by that mass to compete with the electric force between two electrons? When physicists perform this estimate, they are not looking for a number precise to every digit, but for a scale, or order of magnitude, where the quantities become comparable. The result is striking. The required mass is so enormous that it far exceeds the mass of any known elementary particle in 20th century particle physics. It is not like the electron, proton, or any particle in the Standard Model completed in the 1970s. But this does not collapse the argument. On the contrary, it points to the next direction, because that mass is not some new object brought in from outside. It is precisely the equivalent mass of the energy we are forced to pump into the system when compressing it into a sufficiently small region of space. When we convert this required effective mass into energy, using the E equals sign Mestiqued relation given by Albert Einstein in 1905, we obtain an enormous energy scale far beyond the reach of today's most powerful accelerators, like the LHC at CERN, which only access energy scales exploited since the early 21st century. But the key point is not the technological limit. It is the theoretical consequence. To make gravity and electromagnetism comparable, we must reach an energy regime where familiar concepts of particle physics begin to lose validity. In that regime, space can no longer be treated as a smooth, passive backdrop, where particles simply interact via fixed forces. Instead, the structure of space itself begins to respond to the energy and mass it contains. The estimate of the scale where the two forces become comparable is therefore not merely a question of force strength. It is a crucial theoretical signpost, indicating that we are approaching a realm where quantum mechanics, relativity, and gravity can no longer exist as separate pieces, and where the foundational assumptions about being able to subdivide space and increase energy indefinitely begin to be seriously questioned. So what if we don't stop there? What if we ignore those implicit warnings from the order of magnitude estimates and keep pushing this physical system even further, continuing to cram energy and mass into an ever smaller region of space? What really happens then? At this stage, a very familiar temptation of classical thinking emerges. If a trend has held true over some range, perhaps it will continue forever. If gravity grows stronger as effective mass increases, then we just need to keep increasing the energy. If we want to see deeper, we just need higher energy probes, smaller distances. But it is precisely here that physics begins to say no, and it says it very decisively, because reducing distance is not merely changing a parameter in an equation. It is directly intervening in the structure of the space where all phenomena take place. As the distance between particles continues to shrink, the energy required to confine them does not increase linearly, but rises ever more rapidly, a fact physicists recognized right from the early quantum analyses of the 20th century. This energy is not an abstract number. It is a real physical quantity, and according to the relation E equals sign MC quest, published by Albert Einstein in 1905, it carries mass, and therefore carries gravity. At some threshold, the increase in effective mass becomes so large that we can no longer treat gravity as a weak force trailing behind the others. Gravity begins to react forcefully, and that reaction can no longer be described by Newtonian force arrows from 1687. The space surrounding that high energy region begins to curve in a real way, precisely in the language Albert Einstein introduced in general relativity in 1915, where gravity is no longer an ordinary force, but the curvature of space-time itself. According to this theoretical framework, when we pack too much energy into too small a region of space, we do not merely increase the attractive force between particles, we deform the very space-time in which they exist. That deformation does not rise harmlessly to infinity. It can lead to a grave consequence. Space closes in on itself and collapses under the weight of the very energy we have forced into it, an idea seriously discussed in gravitational physics since the first half of the 20th century. This exposes a fundamental truth that all linear trends overlook. There is no infinite pathway that allows us to descend to ever smaller scales simply by increasing energy. Not because we lack cleverness or because technology is not advanced enough, but because the very structure of reality does not permit it. When we try to go too far down the path of reducing distance and increasing energy, nature does not continue to play by the old rules. It changes the rules of the game. turning space and time from a passive backdrop into dynamic entities capable of reacting and imposing hard limits on what we can observe and achieve. To understand more clearly how gravity responds when mass and energy are compressed to extreme levels, I want to step back for a moment and recall a concept that seems very familiar in classical physics, but plays a pivotal role in this entire story: escape velocity. This concept was clearly formulated in Newtonian mechanics after 1687, when Isaac Newton published the law of universal gravitation, and it answers a highly intuitive question: with what speed must an object be launched to completely escape the gravitational field of a celestial body and never fall back? In the framework of classical gravity, this question is solved by balancing energy. An object near the surface of a celestial body has negative gravitational potential energy, meaning it is trapped in that gravitational field. To escape, it must be given enough kinetic energy to offset the gravitational energy so that its total energy becomes zero. When this calculation is performed, a simple but profoundly deep result emerges. Escape velocity depends directly on the mass of the celestial body and inversely on its radius. The more massive the body, the stronger the gravitational field and the greater the speed required to escape. At the same time, for the same mass, if the body is compressed into a smaller radius, gravity at the surface becomes stronger and escape velocity increases. This relationship gives us an important intuition. Escape velocity not only measures the strength of gravity, but also reflects the degree of mass concentration in space. We can see this very clearly through familiar examples that were accurately measured in the 20th century. On Earth, escape velocity is about 11 kilometers per second, a number that became crucial in aerospace engineering from the late 1950s, when the first rockets were designed to carry humans beyond our planet's gravitational field. On Jupiter, a planet more than 300 times more massive than Earth, escape velocity rises to about 60 kilometers per second. Even though Jupiter also has a much larger radius, the increase in mass still dominates, making escape from its gravity far more difficult. These numbers are not merely illustrative. They show that escape velocity is a direct measure of the imprisonment a celestial body imposes on surrounding matter and energy. But what is most important for our argument is not those specific values, but the trend the escape velocity formula reveals. If we keep the mass fixed and continue reducing the radius, escape velocity increases without any intrinsic limit in Newtonian mechanics. There is no clause in classical theory preventing escape velocity from becoming arbitrarily large, and it is precisely here that a special velocity of nature forces us to stop and rethink the entire picture: the speed of light. Since 1905, when Albert Einstein published special relativity, light has no longer been understood merely as a very fast form of motion, but as the absolute speed limit for all information and physical influence in the universe. No matter can reach or exceed that limit. So what happens if, in the process of compressing mass and energy into an ever smaller region of space, the escape velocity at the surface of that region rises to equal the speed of light? The Newtonian formula itself knows nothing about this limit. It simply continues to allow escape velocity to increase. But relativity forces us to confront an inescapable consequence. If escape velocity equals the speed of light, then even light itself cannot escape that region. And if light cannot escape, then physically, no information from inside can reach the outside. This transforms the concept of escape velocity from a technical detail of classical gravity into an extremely profound conceptual marker. It points to the boundary where continuing to compress space no longer merely increases gravity in a bit stronger way, but begins to fundamentally alter the relationship between one region of the universe and the rest. When we apply this concept to regions of space where energy and mass are compressed to extremes, we begin to see that increasing energy to look deeper is not an infinite path. At some threshold, Space no longer plays the role of a passive backdrop, but reacts decisively. Escape velocity reaching the speed of light is not just a special number. It is a signal that the structure of space-time has entered an entirely new regime where the familiar assumptions of classical physics are no longer sufficient to describe reality. If the escape velocity of a region of space reaches or exceeds the speed of light, what happens next no longer lies within the realm of ordinary intuition. Since 1905, when Albert Einstein published special relativity, the speed of light has been established not merely as the velocity of a specific phenomenon, but as an absolute limit of nature. No material particle, no signal, no physical influence can propagate faster than it. This carries a direct and uncompromising consequence. If escaping a region of space requires a velocity greater than the speed of light, then not only are material particles trapped, but even light cannot leave. To the outside world, that region of space becomes completely dark, not because it is empty or lacks energy, but because no information from inside can escape to tell us what is happening there. It is from this straightforward argument that the concept of the black hole emerges as a logical consequence, not as a mystical idea. A black hole, in the modern physical sense, shaped by general relativity in 1915, is a region of space-time where gravity is so strong that escape velocity exceeds the speed of light, completely isolating everything inside from the rest of the universe. To describe this condition quantitatively, physicists return to Newton's 1687 escape velocity formula and take a decisive step. Replace escape velocity with the speed of light and solve backward for the radius. The result of that calculation was found by Carl Schwarzschild in 1916, only 1 year after general relativity was born, and the quantity obtained is now called the Schwarzschild radius. This radius tells us that for a given mass, if all that mass is compressed inside a radius smaller than this value, the surrounding space-time will curve to the point where light itself cannot escape. Importantly, the Schwarzschild radius depends directly on mass, not on the specific nature of the matter. For Earth, the Schwarzschild radius is only a few millimeters. That means if in a completely unrealistic scenario, Earth's entire mass were compressed into a sphere smaller than this size, our planet would become a black hole. For the Sun, the Schwarzschild radius is about a few kilometers, a number astronomers have used since the mid-20th century to understand the gravitational collapse of massive stars. These numbers show that black holes do not require infinite masses in a vague sense, but only require mass concentration exceeding a very specific, calculable threshold. But what is truly important for our story is not these familiar astronomical examples, but the conceptual role of the Schwarzschild radius in the overall argument. We began by forcing two electrons closer together, passed through quantum mechanics with the 1927 uncertainty principle, witnessed the increase in energy, the conversion of energy into mass via E equals sine mc grad, and the quiet return of gravity at small scales. Now the Schwarzschild radius provides us with a clear criterion to answer when continuing to compress space becomes observationally impossible, because once a region of space reaches the condition for black hole formation, every attempt to observe its internal structure from the outside is completely blocked. We can continue adding more energy, compressing further, but the only consequence is a larger black hole with a larger Schwarzschild radius. The interior information remains completely isolated. Here a profound paradox emerges. Our very effort to probe smaller scales by using higher energy and better resolution leads to the creation of an absolute barrier to observation. The black hole is therefore not only a distant astronomical object, discovered in the 20th century, but also a natural mechanism demonstrating that infinite probing into the deepest structure of space is not something nature allows. And now the crucial realization is that there is no logical leap anywhere in this chain of reasoning. The black hole does not appear as an extraneous element tacked on to the story. It is the direct and unavoidable consequence of persistently pursuing the same question, using the best physical theories we have. When we start with two electrons, elementary particles confirmed to exist independently since the late 19th century, we immediately see that the electrostatic force between them dominates, while gravity is so weak it can be neglected. Weaker by about 10 to the 42, according to the comparison based on Newton's 1687 and Coulomb's 1785 laws. But that picture holds only in the low-energy regime. Since 1927, Werner Heisenberg's uncertainty principle has forced us to acknowledge that confining particles to a smaller region of space inevitably increases the system's energy. And since 1905, Albert Einstein has shown that this energy is not an abstract number, but carries mass through the relation E equals sign mc Gare. As the effective mass of the system increases, general relativity from 1915 tells us that the surrounding space-time will curve. As we continue compressing the two-electron system to ever smaller scales, the increase in effective mass is no longer gentle. It rises so rapidly that gravity can no longer be treated as a minor force. At a certain threshold, the issue is no longer particle interactions, but the stability of space-time itself. When mass is concentrated inside a radius smaller than the Schwarzschild radius, determined by Karl Schwarzschild in 1916, gravitational collapse occurs and a black hole forms. In the context of the two-electron system, this means that if we try to go far enough down the small-scale ladder by increasing probe energy, we are no longer simply looking at two electrons. We are creating a new space-time structure where all interior information is completely severed from the outside world. This is a conclusion uncomfortable for intuition, but it is entirely consistent theoretically. There is no point in this chain where physics stops applying. On the contrary, it is the serious application of theories built throughout the 20th century that leads us to this conclusion. And from here, a profound paradox emerges. To probe finer structures of matter, we need higher energy. But that very energy, when compressed into sufficiently small space, creates a black hole that completely hides what we want to observe. In the case of the two-electron system, this means there exists no conceivable experiment that allows us to determine the structure of space at arbitrarily small scales, not because the electron has some hard size, but because space-time itself reacts to our efforts. It collapses. And when that happens, familiar concepts like distance, position, and even time lose their ordinary physical meaning. The two electrons here are merely a minimalist example, chosen for its simplicity. The mechanism exposed is universal. Whenever we try to cram enough energy into a sufficiently small region of space, gravity responds by erecting an absolute barrier. That barrier is the black hole. In this sense, black holes are not only distant astronomical objects discovered in the 20th century. They are the extreme manifestation of a deeper principle. Space-time does not allow itself to be probed infinitely. When we try to go too far, nature does not answer with finer details, but with the complete silence of an event horizon. And at this point, the entire chain of reasoning that we have patiently built over more than a century of modern physics development begins to close in on itself into an inescapable paradox, one that does not arise from philosophical speculation, but from the very core principles established through mathematics and experiment. That paradox can be stated very simply. To observe ever smaller structures in nature, we are forced to use ever higher energies. This principle has been clearly understood since the early 20th century, when scattering experiments showed that to probe smaller distances in matter, we need particles with higher energy corresponding to shorter wavelengths according to quantum mechanics. In the familiar world, this seems harmless. To see more detail, we improve resolution. But since 1927, with Werner Heisenberg's uncertainty principle, we know that observation is no longer a passive act. Determining position within a small region of space forces the system to pay a price through increased momentum uncertainty, that is, increased energy. That energy does not vanish after the measurement. Since 1905, Albert Einstein's special relativity has shown that energy carries mass through the relation E equals sine mc squared. This means that every effort to achieve higher resolution increases the effective mass crammed into the region of space being probed. At first, at the low energy scales, familiar to 20th century particle physics, this increase is very small and can be neglected. But as the observed distance continues to shrink, the required energy rises so rapidly that it is no longer a minor correction. And as mass increases, gravity increases accordingly, just as predicted by general relativity in 1915. Here, a closed loop forms. Observation demands energy. Energy creates mass, and mass makes gravity stronger. But gravity is not simply an added force. When it becomes strong enough, it begins to restructure space-time itself. Space curves, time slows, and when energy is compressed beyond a calculable threshold, a black hole forms, exactly according to the condition discovered by Carl Schwarzschild in 1916. The consequence of this is radical. The very act of observation, when pushed to its extreme limit, creates a physical object that completely hides the information we are seeking. Once a black hole appears, every signal from inside the event horizon is cut off. Light cannot escape. And since light is the carrier of information, the internal structure becomes physically inaccessible from the outside. We can keep pumping in more energy, keep trying to look deeper, but the only thing achieved is a larger black hole with a wider event horizon and an even broader hidden information region. Instead of revealing more detail, nature slams the door on information shut. This is the central paradox. The harder we try to observe deeper, the more certainly we create the conditions that make observation impossible. What is important is that this paradox does not depend on the technological or technical limits of the 21st century. It does not say that our instruments are not yet good enough. It says that even in an ideal thought experiment, where we have complete control over energy and precision, the laws of physics still force us to confront this limit. There is no way to observe a region of space smaller than a certain scale without causing that very region to collapse into a black hole. When that happens, the concept of observation loses its ordinary meaning. We are no longer an observer standing outside looking at nature. We become an agent, creating an absolute barrier to information. This shakes a profound assumption that science has carried since the Enlightenment, that with enough patience and enough tools, we can know everything. Here, nature answers that there are questions that cannot be answered by looking more closely, because the very act of looking radically alters the structure of reality. In this context, the black hole is not merely a strange astronomical object discovered in the 20th century. It is the physical symbol of the limit of cognition, the mechanism space-time uses to set a boundary on what can be known. The question now is no longer whether a limit exists, but where that limit lies. If compressing energy into space ultimately inevitably leads to black hole formation, then there must exist a characteristic scale, a very specific distance, where this process becomes unavoidable. In other words, at what length do all efforts to probe deeper automatically end the possibility of observation? Remarkably, this question does not require us to invent a new theory right away. By seriously combining the three pillars built in the 20th century, quantum mechanics formed between 1900 and 1930, Albert Einstein's special relativity of 1905, and general relativity of 1915, along with gravity, we can already determine that scale. The argument proceeds in a very tight logical sequence. To observe a structure at distance r, we need a probe particle with a wavelength no larger than r. According to quantum mechanics, this means the particle must carry ever higher energy as r decreases. Werner Heisenberg's uncertainty principle, announced in 1927, tells us that confining a particle to a very small region of space inevitably leads to an increase in energy. Special relativity says that energy is equivalent to mass. And general relativity tells us that if this mass is crammed into a region of space smaller than the corresponding Schwarzschild radius, the quantity discovered by Carl Schwarzschild in 1916, a black hole will form. When we combine these relations and ask at what distance the energy needed to probe r is simultaneously large enough to create a black hole whose Schwarzschild radius is also approximately r, a very special number appears. That distance is on the order of 10 to the minus 35 meters. This is a length so small it defies all intuition. Smaller than the size of an atomic nucleus by billions of trillions of times, and smaller than any scale that particle accelerators like the LHC at CERN, operating since 2008, can reach. This distance is called the Planck length, a quantity introduced by Max Planck as early as 1899, when he studied the fundamental constants of nature. What is important is not only the specific value of the Planck length, but its profound physical meaning. It is not the size of a particle or an object, but a theoretical boundary where the three great domains of physics, quantum mechanics, relativity, and gravity, are forced to converge. At scales much larger than the Planck length, we can separate these theories relatively safely, but at the Planck length, that separation collapses. The uncertainty principle cannot be ignored because we are at the extreme microscopic scale. Relativity cannot be ignored because the involved energy is enormous, and gravity cannot be ignored because the curvature of space-time itself determines whether the concept of distance still has meaning. The Planck length is therefore not just a small number. It is the sign of a phase transition in the way nature operates. It marks the boundary where the concept of smooth, continuous space that we are accustomed to using begins to lose validity. Below this scale, saying that two events are separated by a definite distance no longer carries clear physical meaning, because any attempt to measure it would require energy large enough to collapse the very region of space being measured. This shows that the Planck length is not a limit due to lack of technology or understanding, but a limit encoded directly into the structure of modern physical laws. The Planck length, with a value of approximately 1 part in 10 to the minus 35 meters, is not a barrier due to the weakness of 21st century technology, nor is it a sign that humans are not yet smart enough or not yet sophisticated enough to look deeper. The history of science shows that many limits once thought absolute were later surpassed. Before the 17th century, human senses were considered the ultimate limit of observation until Galileo Galilei built a telescope in 1609 and opened an entirely new universe. Before the 19th century, the structure of matter was regarded as continuous until the microscope and later atomic theory revealed the microscopic world. But the Planck length does not belong to the same category as those historical limits. It does not say we cannot measure it yet. It says in principle it cannot be measured. The reason is very clear and rests entirely on established laws. Any measurement no matter how perfectly imagined, must obey the same physical laws we used to derive the Planck length itself. To measure a smaller distance, we need a signal with a shorter wavelength. According to quantum mechanics developed from 1900 to 1930, this means using higher energy. Albert Einstein's special relativity of 1905 says that energy carries mass. And general relativity of 1915 says that when mass is concentrated into a sufficiently small region of space, space-time curves so strongly that a black hole forms, according to the condition discovered by Karl Schwarzschild in 1916. There is no escape from this loop. We cannot measure more cleverly to avoid it, because the problem lies not in the finesse of the measurement, but in the foundational connection between energy, mass, and space-time. In this sense, the Planck length is a principled limit, encoded in the structure of nature, not a practical limit waiting to be overcome. It marks the point where the concept of measurement, as we understand it from classical physics, begins to lose meaning. Below that scale, there is not a smaller world waiting to be discovered, but a realm where the foundational concepts of measurement, distance, position, temporal sequence, become ambiguous or inconsistently definable. Asking what lies below the Planck length may be like asking, what is north of the North Pole? The question uses concepts valid in one domain, but loses meaning when applied beyond that domain. The Planck length is therefore not a physical wall that can be broken with stronger technology, but a conceptual boundary where our current physical language ceases to function. And this is not a failure of science, but a profound achievement. Recognizing the existence of a principled limit shows that our theories, quantum mechanics, relativity, and gravity, have been pushed to their highest possible consistency. Only when we understand the full strength of our theories can science point out where the old concepts are no longer sufficient. In that sense, the Planck length does not say, stop asking. It says, ask in a different way, inviting us to seek a new theoretical framework where space and time are no longer understood as continuous fabrics that can be subdivided infinitely, but as a deeper structure compatible simultaneously with quantum mechanics, relativity, and gravity. In fact, we can arrive at exactly the same scale by a completely different path, even more abstract, yet no less convincing theoretically: dimensional analysis. When physicists try to understand the deepest limits of nature, they often return to the fundamental constants, the numbers that recur in the most successful theories throughout the 20th century. In this case, three constants play the central role. The first is the reduced Planck constant, denoted Kraft, introduced into physics in the early 20th century with the birth of quantum mechanics, establishing the link between energy and frequency, momentum and wavelength. The second is the speed of light, c established as a universal constant in 1905 in special relativity, linking space to time and energy to mass. The third is Newton's gravitational constant, g appearing in 1687 in the law of universal gravitation, characterizing the strength of gravity and the extent to which mass and energy curve space-time. Remarkably, these three constants are not minor technical details. They are the very foundations of the three great pillars of modern physics: quantum mechanics, relativity, and gravity. The pioneering question Max Planck posed as early as 1899 was, can these fundamental constants be combined to construct natural scales that depend on no particular object, experiment, or artificial system of measurement? In other words, can length, time, or mass be determined purely from the structure of physical laws, rather than from a ruler or a specific phenomenon? Dimensional analysis allows us to approach this question directly and rigorously. Each constant carries its own physical units. Kurzsech has units of energy times time, or equivalently mass times length squared over time. T has units of length over time, and G has units such that when combined with mass and distance, It yields a gravitational force. The problem is to find a combination of coset, c, and g, such that the final result has units of length only, with no leftover time or mass. This may sound like a dry algebraic exercise, but its result carries profound physical meaning. When we carefully perform this combination, we discover that dimensionally there is only one unique way to create a quantity with units of length from those three constants, and the quantity obtained is precisely the Planck length, with a value of approximately 10 to the minus 35 meters. What is important here is that we do not need to mention the electron, speak of black holes, or imagine any observational experiment. The unit structure of the fundamental constants alone forces us to acknowledge the existence of a special length scale. This carries very strong meaning. The Planck length is not the accidental product of a specific argument, but the inevitable consequence of the coexistence of the three pillars of physics. It appears as soon as we accept that the world obeys quantum mechanics, obeys relativity, and has gravity. Even more remarkable is that two completely independent paths, one based on a thought experiment about observation energy and black holes, and one purely based on abstract dimensional analysis, converge on the same result. Both point to the same scale, the same tiny number, the same boundary where familiar concepts of space and time begin to collapse. In science, when independent lines of reasoning lead to the same conclusion, that is strong evidence that we are touching a foundational feature of reality. This convergence gives us reason to believe that the Planck length is not a convenient choice or an artifact of method, but a deep characteristic of nature, and that illuminates the nature of the limit we are discussing. If the Planck length emerges both when we analyze the physical process of observation and when we merely look at the unit structure of the fundamental constants, then clearly this is not a limit due to circumstance or technology, but a limit deeply inscribed in the laws themselves. Two paths, one result, and that result tells us that space cannot be subdivided infinitely in the way classical intuition once suggested, and that any description of the world at deeper scales will force us to fundamentally change the way we think about space, time, and their relationship. So is there a corresponding mass scale? And the answer, once again, is yes. Using the very same dimensional analysis method we just employed, when combining the three fundamental constants, quasat, c, and g, the reduced Planck constant of quantum mechanics, the speed of light of relativity, and Newton's gravitational constant appearing from 1687, but this time not to produce a unit of length, but to produce a unit of mass, we obtain a quantity called the Planck mass. This quantity was first systematically identified by Max Planck in 1899, when he realized that the fundamental constants of nature could define natural scales independent of any specific object. Numerically, the Planck mass is on the order of a few tens of micrograms, that is, about 1/100th of a milligram. In everyday life, that is an extremely small mass, so small that it is comparable to the mass of a fine dust particle, or even to the mass of a flea egg. We could place it on the tip of a finger and not notice its presence at all. But it is precisely here that our intuition is once again deceived. Because in the microscopic world, where the masses of elementary particles are measured by numbers so small they are hard to imagine, the Planck mass is an enormous quantity, the mass of an electron. The particle discovered by J.J. Thomson in 1897 is smaller than the Planck mass by tens of trillions of times. Even the proton, a particle nearly 2,000 times heavier than the electron, and clearly identified in early 20th century experiments, remains utterly negligible compared to the Planck scale. This creates a strange inversion. A mass that is very small, by everyday standards, is extremely large by the standards of quantum physics. And it is precisely this inversion that gives us an important clue to the profound physical meaning of the Planck mass. The Planck mass is not the mass of any specific particle in nature, nor is it the mass of an object we could manufacture or directly observe in experiment. It emerges as a scale, a boundary marker, where the familiar concepts of physics begin to switch roles. To see this more clearly, let us recall the argument about compressing energy into a small region of space. As energy increases, effective mass increases accordingly. As Albert Einstein's special relativity pointed out in 1905, as effective mass increases, gravity becomes stronger, just as general relativity in 1915 predicts. The Planck mass marks the level at which the gravity of a concentrated amount of energy can no longer be neglected in a quantum description. In other words, if we have a system with a mass approximately equal to the Planck mass confined to a very small region of space, we can no longer describe it using ordinary quantum mechanics alone, nor can we treat spacetime as a flat, passive backdrop. At this mass scale, gravity becomes strong enough to be on equal footing with quantum effects. This is why the Planck mass is often regarded as the mass scale at which gravity becomes quantum, in a very direct sense. In the familiar particle physics of the 20th century, gravity is so weak that we can completely ignore it when describing interactions between particles. But at the Planck mass, that neglect is no longer valid. Gravity is no longer a faint background effect, but an inseparable part of the dynamics. A more intuitive way to picture it is this. If we try to confine a Planck mass into a region of space on the order of the Planck length, about 1 part in 10 to the minus 35 meters, then that region will sit right on the verge of black hole formation, according to the Schwarzschild radius condition, determined by Carl Schwarzschild in 1916. This is no coincidence. The Planck mass and the Planck length are dimensionally constructed to go together. They jointly describe a threshold where energy, mass, and spacetime merge inseparably. This shows that the Planck mass is not just a number in a table of physical constants, but an indicator of the limit of familiar concepts. Below the Planck mass scale, we can speak of quantum particles moving in an almost flat space. Above that scale, if we try to concentrate mass into a sufficiently small region, space no longer plays a passive role, but reacts violently. And it is precisely that reaction that sets a limit on what we can say about the microscopic structure of reality. What is interesting is that the Planck mass also illuminates a point that intuition often overlooks. When talking about the extreme scales of nature, we usually think of quantities that are very small. The Planck length is extremely small. The Planck time is extremely small. But the Planck mass is not small in the everyday sense. It occupies a strange position where the notions of small and large switch places depending on the context. This suggests that at the deepest scales, our familiar classifications, microscopic and macroscopic, small and large, no longer retain their original meaning. The Planck mass thus becomes an important reminder. The limit of space-time is not just a matter of distance or time, but also a matter of energy and mass. When mass reaches the Planck scale, space and time are no longer a neutral stage for physical phenomena, but become dynamic entities that react strongly to what they contain. And it is precisely at this intersection that the picture of the fundamental limits of reality begins to emerge clearly. In modern cosmology, we often speak of the Big Bang as a starting point, a moment when space and time began to unfold, and matter and energy appeared in an extremely hot and dense state. The framework for this view was laid in 1915, when Albert Einstein completed general relativity, allowing the description of space-time dynamics. Based on those equations, cosmologists from the first half of the 20th century were able to run the history of the universe backward, from the present into the past, describing the expansion discovered by Edwin Hubble in 1929, the cooling of the universe, the formation of elementary particles in tiny fractions of the first second, then atoms, stars, and galaxies over the subsequent billions of years. However, as we continue tracing backward in time to ever earlier moments, we soon realize that this journey cannot continue indefinitely. There is a point at which our theoretical tools begin to contradict themselves, and that point is the Planck epoch, around 10 to the minus 44 seconds after what we call the Big Bang. At this time scale, the quantities used by general relativity, energy density, space-time curvature, become extreme. If we mechanically extrapolate Einstein's equations backward, we encounter a singularity where density and curvature rise to infinity. But in theoretical physics, such a singularity is not understood as a physical entity existing in nature, but as a signal that the theory has been pushed beyond its valid domain of application. It tells us that general relativity, despite its outstanding success at astronomical scales throughout the 20th century, was not designed to describe the extreme conditions where quantum effects of gravity cannot be neglected. The Planck epoch is precisely the regime where the three pillars of modern physics, quantum mechanics, formed between 1900 and 1930, Einstein's relativity and gravity, all simultaneously demand consideration, yet we lack a unified framework to combine them consistently. This leads to a peculiar situation. We have relatively clear pictures of the universe at very early times after the Big Bang, such as the inflationary models proposed from the early 1980s, or Big Bang nucleosynthesis, occurring a few minutes after the Big Bang. But all those descriptions begin after the Planck epoch. They all assume the existence of a sufficiently stable space-time background for familiar concepts like temperature, density, and time to be defined. Right at the Planck epoch, that assumption is no longer secure. To date, no complete theory exists that allows a reliable description of what really happens during this phase. Different candidates, from attempts to quantize gravity to models assuming a new microscopic structure of space-time, offer very different pictures, but none has yet been directly verifiable by observation or experiment. What is important to emphasize is that this absence is not a local failure of cosmology, but a profound sign of the limit of classical description. In the Planck epoch, not only do specific equations lose validity, but the very way we think about describing a physical state must be re-examined. If time is no longer a fundamental parameter, then saying the universe evolves over time may no longer be an appropriate way to express it. Perhaps at the Planck scale, the universe does not happen in the ordinary sense, but exists in a state where the notion of before and after is not clearly defined. From this perspective, the familiar question, what happened before the Big Bang, becomes suspect, because it implicitly assumes that the concept of before still has meaning at the Planck scale. Rather than viewing the Big Bang as an event occurring in time, it may be more reasonable to regard it as a boundary of description, a point where classical concepts of space and time begin to emerge as effective quantities. The Planck epoch, in that sense, is not necessarily the first moment of the universe, but the boundary where the concept of time begins to acquire physical meaning. This does not make cosmology less convincing. On the contrary, it opens a new depth. It shows that the deepest questions about the origin of the universe are not only about initial conditions, but about the nature of the very concepts, space, time, and causality, that we use to pose the questions. So in the end, is space-time truly continuous as we have assumed for centuries? Or at its deepest level, is it composed of some discrete units? For most of the history of physics, from 17th century classical mechanics to early 20th century relativity, the continuity of space and time was almost unquestioned. The equations of Isaac Newton in 1687, or of Albert Einstein in 1905 and 1915, all rely on quantities that can vary smoothly, can be subdivided infinitely, and differential equations became the default language for describing nature. Space was viewed as a smooth manifold, time as a continuous flow without jumps. But as we approach the Planck scales, these assumptions begin to be questioned. The idea that space-time may be discrete is not an arbitrary speculation, but arises from the very experience of quantum mechanics built between 1900 and 1930, where many quantities once thought continuous turned out to be quantized. The energy of electrons in atoms, first described by Niels Bohr in 1913, takes only discrete values. Angular momentum does the same. This suggests that space and time, when probed at sufficiently small scales, may also no longer be continuous, but composed of atoms of space-time, with the Planck length of about 10 to the minus 35 meters, serving as the characteristic size of those units. However, when seriously considering this possibility, a profound conceptual obstacle immediately appears, and it comes from special relativity. One of the core principles of the 1905 relativity is that there is no absolute length scale, the same in all reference frames. Lengths depend on the state of relative motion through the Lorentz transformation. If one observer measures a distance on the order of 10 to the minus 35 meters, another observer in relative motion will measure a different value. This leads to a very uncomfortable question. If the Planck length is the smallest unit of space, in which reference frame is it defined? And how can the notion of discrete spatial cells be compatible with the principle of relativity, which denies the existence of a privileged reference frame? This is not a minor technical detail, but a foundational challenge. Some physicists are willing to accept that at the Planck scale, Lorentz symmetry may need to be modified or extended, treating it as an effective description, valid at large scales, but not necessarily at the deepest microscopic level. Such approaches often lead to models where space-time has a discrete structure, but at the cost of weakening one of the central principles of relativity. Conversely, many other physicists regard Lorentz symmetry as too successful to abandon, since it has been verified with extremely high precision in experiments throughout the second half of the 20th century. They seek frameworks in which space-time remains mathematically continuous, but measurement is limited by deeper principles, such as the fact that any attempt to probe below the Planck scale inevitably leads to gravitational collapse and black hole formation. In this view, the Planck length is not the size of a brick of space, but an operational limit. We cannot assign physical meaning to distances smaller than that, even if mathematics allows us to write them down. The debate, therefore, is not only about continuous versus discrete, but directly concerns the nature of space-time. If space-time is discrete, then familiar geometric concepts like curvature, derivatives, or distance may be mere approximations that emerge when considering vast numbers of fundamental elements, just as a solid appears continuous at large scales, but has atomic structure at small scales. If space-time is continuous but cannot be probed below a certain scale, then that continuity may be a genuine property of reality, even if we can never directly test it. What makes this issue particularly difficult is the absence of experimental data. Planck scales lie far beyond the reach of any direct experiment we can envision in the foreseeable future. Thus, the current debate relies primarily on the internal consistency of theories, the ability to reconcile known principles, and indirect consequences that may be found in extremely precise astronomical observation. To date, there is no consensus in the scientific community about whether space-time at its deepest level is continuous or discrete. Both approaches have strong arguments and serious difficulties, and this is not a sign of deadlock, but the familiar state of science when standing at a new frontier of cognition. The history of physics shows that such questions often require a profound conceptual shift rather than a minor adjustment to equations. And perhaps the final answer will not lie fully at either extreme of continuous or discrete, but in a more subtle understanding, where space-time does not perfectly fit any intuition we currently possess. Our current theories, despite having been verified with extraordinary precision in the 20th and early 21st centuries, are still insufficient to describe reality at its deepest level. This is not a criticism of quantum mechanics, built from Max Planck in 1900 through the late 1920s, or of Albert Einstein's general relativity, completed in 1915. On the contrary, it is precisely because these two theories are so successful in their domains of application that their limits are revealed so clearly. Quantum mechanics describes the microscopic world with astonishing accuracy, allowing us to predict atomic spectral structure, electron behavior, and electromagnetic, weak and strong interactions with errors so small that many figures are verified to 10 or 12 decimal places. General relativity, conversely, has passed every observational test from the perihelion precession of Mercury to the detection of gravitational waves in 2015, and provides a consistent picture of gravity, the curvature of space-time, and the evolution of the universe on large scales. The real problem arises only when we are forced to use both frameworks at the same time. At the Planck scale, gravity can no longer be treated as a weak effect that can be ignored in a quantum description, and quantum effects are no longer small corrections on a smooth geometric background. The two physical languages we are accustomed to using begin to overlap, but do not mesh. Equations become uncontrollable. Quantities tend to explode to infinity, and conceptual paradoxes appear ever more densely. This is not a sign that nature is contradictory, but a sign that our descriptions have reached the boundary of their validity. It is precisely at this point that the need for a quantum gravity theory arises not as a luxury ambition, but as a logical necessity. If we want to speak consistently about the Planck epoch of the universe, to understand what really happens when energy is compressed into extremely small regions of space, or to describe the interior of black holes beyond quantities measured from the outside, then a new theoretical framework is unavoidable. However, the history of science also teaches us to maintain a sober and neutral attitude toward this need. Recognizing that a new theory is required does not mean we already know what that theory will look like. Before quantum mechanics emerged, early 20th century physicists knew that classical mechanics could not explain blackbody radiation or atomic spectra, but it took decades of experimentation, debate, and mistakes for a new framework to gradually form. The current situation with quantum gravity has many parallels. We know there is a real problem at the intersection of quantum mechanics and gravity, but we do not yet know the right language to describe it. Many different approaches are being pursued. Some attempt to directly quantize gravity, treating space-time as a dynamic quantum entity. Others start from quantum mechanics and view gravity as an emergent phenomenon at large scales. Each direction achieves local successes, but also encounters serious difficulties. And to date, none has been confirmed as the correct path. That is why a scientific attitude of neutrality is essential. Neutrality here does not mean indifference, but a readiness to admit that we do not yet know the answer, that nature has no obligation to conform to our intuition or to mathematical structures we find beautiful. A quantum gravity theory, if it exists, may force us to abandon or reinterpret concepts once thought foundational, such as space, time, or even causality. At the same time, the absence of a complete theory does not render what we have already learned meaningless. On the contrary, the verified successes of quantum mechanics and general relativity are the benchmarks that any new theory must reproduce in the appropriate domains. A quantum gravity framework cannot destroy those achievements, but must encompass them as special cases. This makes the task more difficult, but also clearer. We are not seeking a complete replacement, but a profound extension. The need for quantum gravity is therefore not merely the need to resolve a few technical paradoxes, but the need to understand how the extreme scales of nature, the Planck length, Planck mass, Planck time, fit together in a deeper structure. Finding that structure may take many decades, even generations, but scientifically, it is the natural next step in the long tradition of pushing theories to their limits and learning from their very collapse. So why, after centuries of scientific progress, must we still acknowledge that there are things we cannot know, scales we cannot reach, questions we cannot yet answer? I believe it is precisely here that we need to pause and think a little more slowly, because recognizing limits is not a sign of failure, but a sign of intellectual maturity. In the history of science, every time a genuine limit has been clearly identified, it has typically been the moment when human understanding steps into a deeper layer. Before 1687, when Isaac Newton published the Principia, humanity lacked a clear quantitative concept of motion or gravity. The world was explained through intuition and natural philosophy. Newton established precise laws, but that very framework later revealed its limits when velocities approach the speed of light or gravitational fields become extremely strong. In 1905 and 1915, Albert Einstein did not reject Newton, but showed that Newton's laws are excellent approximations in the realm of low speeds and weak fields, yet no longer hold when pushed beyond that domain. Similarly, quantum mechanics, formed between 1900 and 1930, with contributions from Max Planck, Niels Bohr, and many others, did not arise because classical physics was inadequate, but because classical physics had been so successful that its contradictions only emerged at the most extreme scales. Seen in this light, the Planck limits the length on the order of 10 to the minus 35 meters, and the time on the order of 10 to the minus 44 seconds are not walls slamming shut the path of cognition, but milestones showing how far we have come. The fact that we can state with precision that below the Planck length the concept of space loses operational meaning, or below the Planck time the notion of before and after becomes blurred, is already an astonishing intellectual achievement of the 20th century. That is not vague ignorance, but very specific knowledge about where our concepts cease to function. Science does not mature by declaring it can answer every question, but by knowing exactly which questions can be meaningfully posed within the current framework and which lie beyond it. In the philosophy of science, there is an important distinction between we do not yet know and we cannot know in this way, and the Planck limits belong to the second category. They do not say that reality ends there, but that the conceptual tools we are using, continuous space, continuous time, classical measurement, are no longer adequate when stretched to those scales. Every clearly identified limit opens up new questions at a deeper level. If space and time are no longer foundational at the Planck scale, what structure replaces them? If gravity cannot be described classically in the quantum regime, what is its correct form? These questions only become sharper when we understand precisely where we stand. From that perspective, limits are not the end point of science, but the necessary condition for science to continue advancing meaningfully. If there were no limits, if every concept could be extended indefinitely without contradiction, science would become a self-satisfied system with no drive to change. It is precisely the breaking points, where current theory no longer works, that mark the true beginning of scientific creativity. This also carries a broader lesson about humanity's place in the universe. We evolved to survive at a very specific scale, and it is no surprise that our intuition fails at extremely large or extremely small scales. What is astonishing is that through mathematics and reasoning, we can still reach into those realms and even determine the point where that very reach must stop. Recognizing our limits, in this sense, does not diminish humanity, but reveals the sophistication of human intellect. We not only know, but also know what we cannot know, and in what way. If at this moment we could declare definitively whether space-time is ultimately continuous or discrete, whether quantum gravity must have this structure or that, then very likely we would have misunderstood the nature of the problem. The questions posed by the Planck scales, with length on the order of 10 to the minus 35 meters, and time on the order of 10 to the minus 44 seconds, first identified from fundamental constants by Max Planck in 1899, are not questions that can be resolved quickly with a neat calculation or a single experiment. They touch the foundations of how we describe reality. Is space an independently existing entity, or merely a concept that emerges from deeper structures? Does time truly flow, as our biological intuition suggests, or is it merely an ordering of events? And does the concept of causality, deeply embedded in physics since Newton, retain its meaning when the distinction between before and after becomes blurred at the Planck scale? In the history of science, from the 17th century with Newton to the early 20th with Einstein, science has never advanced by closing questions, but by refining them. Vague questions are gradually replaced by sharper, more precise, and sometimes more uncomfortable ones. The journey to the limits of space-time is a classic example of that process. Initially, humans simply wanted to know what matter is made of and what forces govern its motion. But the deeper we went, especially after Albert Einstein introduced general relativity in 1915, and quantum mechanics was completed between 1925 and 1927, the more we were forced to ask not only about matter, but about the very stage on which matter exists. And when that stage begins to tremble under the pressure of extreme energy scales, the question is no longer what happens there, but are we using the right concepts to ask the question at all? In that spirit, the absence of a final, definitive answer does not make the scientific picture incomplete. On the contrary, it keeps it alive. A science that declares its mission complete is a science that has lost its creative drive. Conversely, a science that clearly knows its own open questions, such as the nature of space-time at the Planck scale or the correct structure of quantum gravity, is a science in its healthiest state. The Planck scales in this sense are not the end of understanding, but milestones pointing to where the dialogue with nature becomes more refined. They force us to abandon the complacent confidence that familiar concepts can be applied unconditionally at every scale, and to accept that reality may be far richer than any simple picture we have ever drawn in the past century. What I find particularly admirable is that the spirit of scientific curiosity does not weaken when facing limits, but on the contrary, becomes deeper. This curiosity no longer takes the naive form of finding one more precise number, but assumes the mature form of re-asking foundational questions. It drives 21st century physicists to think seriously about whether space and time are fundamental constituents or merely emergent concepts, much like temperature or pressure in statistical physics. It encourages diversity in approaches, from bold ideas to cautious analyses, and accepts that the path to understanding may be long, winding, and unpredictable. Looking to the future, the only thing we can say with certainty is that research into quantum gravity and the deep structure of space-time will continue to be one of the most challenging and promising fields of physics for many decades to come. Major advances may come from increasingly precise astronomical observations, where the universe serves as a vast natural laboratory, or from mathematical breakthroughs that allow the construction of a new language connecting quantum mechanics, relativity, and gravity. Or they may come from an entirely different perspective that we cannot yet imagine. Ending this story without a definitive conclusion may leave some feeling unsatisfied. But for me it is an honest ending, because science, at its deepest frontier, is not a finished book, but an ongoing manuscript, where each generation, from Planck and Einstein to today's physicists, adds new chapters. The open questions about space-time, the Planck epoch, quantum gravity, are not embarrassing gaps, but invitations. They invite us to keep thinking, keep questioning, and most importantly, keep nurturing the curiosity that has always been the deepest driving force of science. If you would like to continue exploring with me the deepest questions about the universe, space-time, and the limits of human knowledge, please subscribe to the channel so you don't miss the next journeys. See you again in upcoming conversations, where curiosity remains the guiding compass.